Hi, welcome back, kiddos. We're working through our ability to understand and model atomic structure. So what we'll be doing in this video is reviewing the models, and then in the next video we will begin to apply the models. At least that's my goal if time is on my side. So let's forge ahead. There was one more quantum number we hadn't finished, and that's a quick one to do. You saw this a little bit already when I was showing you how many electrons can fit into an orbital, and that's the spin quantum number. Now, what happens is that an electron is spinning, and whenever you have a moving particle, it's going to generate its own little magnetic field. And when these are placed in an external magnetic field, the first one going in will align with the magnetic field, and the second one will line up going against the magnetic field. This one is lower energy, so the up arrow goes in first, and then the down arrow. Okay, they don't say it's degenerate. We will talk about that having the same energy, but it is a little bit easier to go in with the magnetic field than against the magnetic field. So this is plus 1/2 and this is minus 1/2. And so that's the spin quantum number. Now let's start taking a look at some of the models and some of the things we will have to do to ensure that we don't violate the model. So before we build into that, let's make sure we understand how electrons can go in. So the first question said, what's the maximum number of electrons in a P? Make sure you underline this word, because questions are going to try to trip you up in terms of whether it's a sublevel, an orbital, or an energy level. If it's the sublevel, remember P sublevel had 3 orbitals, so 6 electrons. The next one said how many electrons go in the d orbital. All orbitals are created equal in a sense that they all hold 2 electrons. Whether it's an s orbital, a p orbital, or a q orbital, they hold 2 electrons. Now, what's the maximum number of electrons in energy level n equals 4? Well, there's a couple of ways you can do it. You can remember the formula 2n squared. All right, so that's the number of electrons. That'd be 32. Or you can remember that if n is equal to 4, we can have s, we can have p, we can have d, we can have f. S has 2, p has 6, d has 10, f has 14. So if you add those up, that's 24, 32 electrons. All right, now let's take a look at these. Indicate whether or not the following orbitals exist. And if they can't, tell why. Well, 3p exists, because if n is equal to 3, that means L can have S, P, and D. So that one's okay. 4s. Well, if n is equal to 4, what L can be is S, P, D, F, right? 4 and 4. 3 and 3. Okay, if n is equal to 2, L can equal S and P. And that last one was okay as well, but this one is not okay because it doesn't go as high as F. And again, it's because we're very close to the nucleus and there's too much repulsion to accommodate that kind of movement. How about 1p? Well, if n is equal to 1, that's what the number 1 in front means, L can equal S, and that's it. It can't be P. So 1p does not exist. Okay? So now, armed with that information, let's take a look at some of our structural models and advantages and disadvantages to those. All right? Now, structure determines function. So if we can come up with some models that will help us understand the structure, then it can also help us build up an understanding of the function. Functions such as bonding, ion formation, whether or not a substance is diamagnetic. In diamagnetic, all of the electrons are paired, So all of the electrons exist in an orbital like that, and it is not attracted to a magnetic field, or if they are paramagnetic, in which case we have one or more unpaired electron, like a p sublevel that would look like that. And that causes the substance to be weakly attracted to an external magnetic field. So those are the kind of properties that we're trying to uncover with our structural models. All right. Now there's going to be some rules, and I'm beginning to see it's going to take me 2 videos to get through this. So let's at least get through our rules before we start, finish all of our diagrams here. Now, why are these rules? It's not like I can tell electrons what to do. These are rules that have been observed. And one of the first one is called the Aufbau principle. That's not a name. It's not a dead guy named Aufbau. That's German for build up. And what we're going to start with is building up the ground state, lowest energy state of an atom that maximizes electron to nucleus attraction. And remember, that means that if we're going to maximize attraction, we want to be closest to the nucleus. All right, so Aufbau means we're going to build up from low energy to high energy. Here's the problem, is that as you get further from the nucleus, these energy levels get a little bit mixed up. And so we're going to see, and you saw in pre-AP chemistry, that we fill the 4s before the 3d. But no worries, because our periodic table will tell us how to do that. So hopefully you remember the Aufbau principle. And again, make sure in discussing these, you're always mentioning attractions to the nucleus and repulsions between electrons. All right, the next one is called Hund's rule. Now, within a sublevel, that's key, we've got to be within a sublevel. What we're going to do, degenerate means same energy orbitals, we're going to put them in unpaired before we pair them. So if this is representing, say, the 2p, so that's a 2p orbital, all right, and then this is 2 separate ones, so that's a 2p orbital in one direction, and here's a 2p orbital in the other orientation. All right, if you notice here, the electrons are playing within the same playground. That's going to have more repulsion. If we put them into 2 separate orbitals, you've got 1 electron moving in here and 1 electron moving in this region of space, and they're not as likely to get near one another, so there's less repulsion. So this is about minimizing repulsive forces, fewer repulsive forces, and that's Hund's rules. In pre-AP, you memorized that you did this. In AP, you have to be able to explain this concept of the repulsive forces. So again, maximizing attractions, minimizing repulsions. And then finally, we have the Pauli exclusion principle. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. Okay? Now, the way we do that is by putting them in, and we saw this before, you put electrons in with opposing spins. So if this was a 2s sublevel and orbital, all right, what do we have? Well, they both have n equal to 2. They both have L equal to s. They're both in the same orbital, but they have different m sub s, or spin quantum numbers. So no 2 electrons can have the same 4 quantum numbers. All right, so this is what we need to help us communicate and build our models that we'll be using. And we'll be doing orbital diagrams, electron configurations, and yes, shell diagrams. So until the next video, this is signing off.